revolution in deductive science, the mathematical calculus with variables having values known with certainty, the derivative and the integral. A basic example of the former is the slope of each, or at each point of a curve, and the area under the curve for the latter. Number 9, revolution, negative philosophy. Immanuel Kant, or maybe Hermann Cohen also, etc. Based on a critique of philosophy, an attack on all philosophy, not by attacking each proof one by one, but an indirect proof arguing that our understanding is incapable of tackling a whole field of problems, showing that the method of the metaphysics of reason leads to antinomies or contradictions, which can only be resolved by postulating a realm of experience phenomena which we can know, and a realm beyond our mind which we cannot know, or pneumona. He claims also that the existence cannot be proven a priori, but Einstein argued against Kant. We can know the world and demonstrated it by creating the theory of relativity. We made use of the fact that we know the equation that speed is the distance divided by the time, that we know the nature of light, and we know the nature of light and speed. So we could define time in a posterior manner, unlike Kant. Instead, time can only be known in a priori manner. Well, Kant had to distinguish between one and phenomena because he wanted to make free will possible, which is very important for us. Kant and Einstein and Maimonides say for religion and other things. But Einstein attacked him indirectly. Einstein's theory was, he made predictions and were confirmed, kind of. So it is a strong attack of Kant. But it's more scientific. Kant was philosophy, more logic versus mathematics. Many schools of philosophy arose after Kant: analytical philosophy, phenomenalism, even pragmatism, etc. Number 10, revolution of non-Euclidean geometry. Like Carl Friedrich Gauss, or Stephen Hawking calls Gauss the greatest mathematician of all time. Bernard Riemann, Karl Weierstrass, Albert Einstein, etc. Some people say that Gauss, Archimedes, and Newton were the greatest mathematicians of all time. Revolution, number 10, revolution of non-Euclidean geometry. Based on the use of curved linear coordinate system, using perpendicular curves as axis instead of lines as axis. Gaussian coordinate systems. An accelerating object moves along a curve or surface, not a line or plane. Using curved linear coordinate system, was able to relate the equation of motion of a particle in an accelerating reference frame to a linear one in general relativity. Einstein was able to choose the center of the surface and connect it to all points on the surface, and then take projections on the coordinate axis. The equation of the motion and distribution of the object was given by the tensor, which is the coefficients, the equation multiplied by axis variables, all equal to 0. The tensors are two coordinate systems that relate according to the ratios of the projections on the axis of the surface in both coordinate systems. I know when I started this system, I had like about 8 or 10, 12 super methods, and then I just add more and more. I think I have about 300. And Einstein needed answers because in general relativity, we have loop contraction and dilation, and even the distribution of the object, it can no longer be represented as a point, but it changes because of motion acceleration. Assuming that Einstein was correct, discuss that another place. Revolution 11. Revolution 10, calculus mathematics. Okay, Ricky, Levi Zadida. Okay, this is the latest mathematics that was invented maybe about 100 years ago, around 1900. It's very interesting. If you're going to do research, if you look at history, if you want to make a big discovery or start a company and make a lot of money, the key thing is to see what is the latest discovery or the latest tool available. For example, this around 100 years ago, the tensor calculus was a new mathematical tool available to mathematicians, physicists, engineers. Also in non-Euclidean geometry, Einstein made use of it to create geometry of relativity. That's how he revolutionized physics. Also, Max Born also used probability in quantum mechanics. And also, a lot of discoveries were made. For example, the telescope was discovered, Galileo made discoveries, and also when the microscope was discovered, made discoveries, and now they're making more discoveries now. And when they discovered the semiconductors, when the transistor, Silicon Valley was created, and it was like gold mine. People were putting companies, making a lot of money building computers, making them cheaper and cheaper, integrated circuits, because somebody elected the transistor. These are Nobel Prize. But that's basically the key how you make a discovery. So right now, maybe it's not that new, but saying new discoveries algorithms. So the revolution, if anybody wants to make a big discovery of this algorithm, I think they even argue that that's maybe how you should revolutionize physics, not with super string theory using strings, but adding algorithms like you have in computer science, adapt the industrial math, adapt to physics, because you have reasoning beings, you have agents like people, even animals, and you have computers. So physics changes with mathematics, just equations in the algorithms, if, then, and branch, and repeat, and all that. Let alone synchronization, all that. Okay, so anyway, so tensor calculus was a new math 100 years ago. Very complicated. If you could study, maybe a few physicists, even mathematicians really don't usually study it. Remember, the revolution in tensor calculus mathematics, relating hypersurfaces in different coordinate systems. The tensor helps determine position and space and time and distribution of an object as a vector. It also defines how a vector in one coordinate system can transform into an associate that tensor in the other coordinate system. This is needed because the observer and the object are often in different coordinate systems. For example, if one is moving accelerating relative to the other being, the relative motion of the two universes makes an observer in each coordinate system perceive events in the other universe differently. Galileo did this on account for relative motion, while he didn't use tensors, they exist yet. Tensors are coefficients of the equations of these surfaces, and there are equations relating these coefficients and their derivatives. One kind of tensor was used in special relativity and another general relativity. For the former both consists of linear, but in the latter, one is curvilinear due to acceleration, for example, and curvature. The energy tensor, for example, the energy tensor and Riemann tensor are occurring in Einstein's field equations. Once we create a separate integral tensor calculus, well, usually you can convert integral equations to differential equations anyway. Tensor equations are independent of coordinate system. Only variable values change. The form of the equations stays the same. Galileo only gave, I think, a transformation for speed, not acceleration. Plus, they didn't use light. That was later by Lorentz and later even Einstein. Okay, by the way, the Einstein's field equation, I think I made a mistake. I think maybe a lot of people did. After many years, I think I realized the Einstein's field equations are not r subscript u being minus 1 half r minus r subscript minus 1 half g subscript u b r is equals to minus scalar t subscript u b, where the fields are gravitational and the electromagnetic field in space and time. Because you said according to Maxwell, we could get rid of mass and charge because we can have independent electromagnetic fields. I think this is predicted in gravitational fields, which were discovered recently. That's the I think that's the grandification equations. Though he said you might be able to reduce it to algebra if quantum mechanics is right. It's not that he has equations of general relativity will be accelerated. The ones that have gravity alone, those are equations of no motion. Gravity is like acceleration for him. So that equation is there for motion, which have just acceleration. Those are the equations of relativity. And he has other ones. You even have the relativistic equation of electromagnetism. You transform those to into account relative motion. But these are special relativity and the electrodynamic equations. Okay. Number 12, evolution in tensor calculus science. This is long. This is from what Aristotle, Alexander